Hey guys, so today we are going to see another topic in critical speeds of shaft, that is secondary critical speeds in horizontal shafts. So centrifugal forces due to unbalanced masses causes primary or mean critical speed. Besides this, in horizontal shafts, large vibrations are seen at a half critical speeds due to the effect of gravity of the mass, and such speed are called secondary critical speed. So in this, let's draw the diagram for secondary critical speeds in horizontal shafts. So let me draw a circle. So suppose we are considering a horizontal shaft, this, so let this shaft have no vibration, therefore its geometric center S coincides with the point of rotation O. So suppose this is the point of rotation and it coincides with geometric center S. Now considering G to be offset by a distance E from S. So considering, suppose this is the center of gravity. So this is the center of gravity. At a distance E. Lies in the first and the fourth quadrant. Uh, so the gravitational force retards the motion, whereas when G lies in the second and third quadrant, the gravitational force accelerates the motion, and the magnitude of the torque is mge cos omega t. So this will be here, the force will be m into g, and this is omega t angle. So the force will be mge cos omega t. So if I is the inertia of the disk, then using this relationship, we can get that torque T is equal to I alpha. So I is moment of inertia and alpha is angular acceleration. Now we know that what is the angular acceleration here. Alpha will be T upon I. So what is the torque here? So torque here is mge cos omega t and divided by I. So the tangential acceleration at g will be f of t and vertical component will be f of t. So suppose this g, it is having a tangential acceleration, so it will be ft. Tangential acceleration will be e into angular acceleration alpha. So it will be mg e square cos omega t divided by I. And tangential force will be ft is equal to m into ft. So it will be m square g e square cos omega t divided by I. Now the vertical component of this force, so this is the tangential force, and the vertical component ftv will be nothing but cos omega t of this force. So m square g e square uh, cos omega t divided by I into cos omega t, so it will be cos square omega t. So our tangential vertical component is m square e square cos square omega t into g by I. So cos square, also what is cos square omega t? So we can write cos square omega t as also 1 by 2 into 1 plus cos 2 omega t. We can write in this form also. The vertical component of tangential force will be ftv is equal to m square e square g into 1 plus cos omega 2 omega t divided by 2I. Okay, So if we multiply this whole term inside the bracket, so what we'll get? So we will get FTV is equal to FTV is equal to m square e square g by 2I plus m square e square g divided by 2I cos 2 omega t, cos 2 omega t. So the first part of this force is constant and causes small additional deflection, and the second part of this force uh, having a frequency to omega, and thus if the shaft runs at a half critical speed, the frequency of the forced vibration occurs at its natural frequency, and this excitation results in large vibration at a half its critical speed. So this is the secondary critical speeds in the horizontal shafts. So I hope you have understood this secondary critical speed in the shaft. So for greater understanding, I will draw a free body diagram for all these forces. So let's draw a free body diagram. So suppose this is O and S, that is center. Now this is the horizontal line, and this is the center of gravity G at a distance E. So this angle is omega t. Now the mass is acting in downward direction, and so uh, let's create a few angles. So suppose this is 90 degree, so this is 90 degree, and this is at an angle omega t. This is an angle at omega t, and this is 90 degree from this. So this force is nothing but tangential force Ft, which is equal to m into f of t. So this is the 90 degree from this angle, so this is the tangential force. Now the components of this force will be in this and this direction. So in this direction, this is this is the vertical component of Ft. So this is Ftv. So this is the vertical component of Ft, and this will be the horizontal component. So this we have found the vertical component, we have found that is Ftv is the vertical component. So this is the main diagram. So I hope you have understood this diagram. So now let's see now example for critical speed of shaft. So uh, a vertical shaft, sorry, example. So I'll just read the example and plot the data. So a vertical shaft is 12.5 mm diameter, uh, rotates rotates in sleeve bearings. So the diameter is given of the shaft, that is 12.5 mm. It is rotating in a sleeve bearings in a disc of mass 15 kg. So it is rotating in a sleeve bearing and a disc of mass 15 kg. So there is a disc and there is also sleeve. 15 kg is attached to the shaft at the mid span. So it is attached at the mid span. So the span of the shaft between the bearing is 0.5 meters. So length is given, so that is 0.5 meters. So the mass center of the disc is 0.5 mm, 0.5 mm from the axis of the shaft. So determine the critical speed of the shaft. So the mass center of the disc is 0.5 mm from the axis of the shaft. So the mass center is given. So what is mass center? So it is center of gravity. So center of gravity is given. It is 0.5 mm from the axis of the shaft. So L1 is equal to L2 is equal to L by 2 is equal to 0.25 meter. E is given, sorry, E is given, that is 0.5 mm. So center of gravity distance Now we have to find the critical speed of the shaft of the rotation. That is omega n we are interested in finding. What is the speed range in the bending stress in the shaft will exceed 125 Newton per mm square? Assume E. So another question is asked. Uh, Another question is asked that what is the speed range in the bending in which the bending stress in the shaft will exceed. So if the bending stress is 125 Newton per mm square and E is given 2 into 10 raised to 5 Newton per mm square, then what is the speed range? So there are two questions. First is omega, to find omega n, and uh, another is to find speed. So that is n. Now here Now here we will use the formula for critical speed of the shaft. So that is y by e is equal to 1 divided by uh, omega n divided by omega whole square minus 1. So this is the formula for critical speed of the shaft. Now what here we are interested, so here we are interested in finding omega n. So we want to find omega n here. So if we can find omega n, so there is our solution. So before that, do we have other parameters? Do we have e? Yes, we have e. Do we have y? No, we don't have y. So we need to find y here. And also we have to find first y. So how we can find y? So y is deflection. So what is the deflection of the shaft here? So how is the shaft here? So the shaft is fixed from both the ends. So it is fixed from both the ends. So the formula for deflection is WL cube divided by 192 EIX. So with this formula we can find the deflection. So do we have W here? So first thing is, do we have W? So what is the W here? So W here is dynamic load. So how we can find W here? So W we can find by the formula, that is, so to find W we know the formula for bending stress. So that is pi by 32 sigma d cube is equal to WL by 8. So do we have sigma? So yes, we have sigma. Do we have D? So yes, we have D. Then so we have sigma, we have D. Do we have L? Yes, we have L. So it is 0.5. So we can find here. So we can find W here because all the terms are known. So the W value will be equal to 383.495 Newton. So after we get W here, so I'm just writing here in above. So it is 383.495 Newton. So once we get W, so we can get here Y, because W we know, L cube we know, E we have, E we have, E is given here. Then Ix. So now what is Ix? So Ix is nothing but polar moment of inertia. So the formula for Ix is pi by 64 d raised to 4. So d we have diameter, that is 12.5 mm. So with the help of that we can find y, and y we will get here, that is 1.04166 mm. So after we get y, we can put here y, and e we have, e is given here. So y by e is equal to 1 upon omega by omega n. So let me rewrite this formula at the end. So y by e is equal to 1 divided by omega n by omega whole square minus 1. Now we have y, we have e. So let me reciprocal this. So this will be E by Y is equal to omega n by omega whole square minus 1. So let me bring 1 on this side. So it will be E by Y plus 1 is equal to omega n by omega whole square. So here E by Y, what is the value? So the value of what is the value of E? So the value of E is 0.5 and the value of Y is 1.04. So it will be, so this is nearly equal to 1.48. So omega n by omega whole square is equal to 1.48. So this value is 0.48 and this plus 1, so it has become 1.48. Now when y is positive, corresponding to the speed omega 1, and when y is negative, so we are considering when I take square root on this side, so it will be plus or minus y. So omega n omega is equal to plus or minus under root of 1.48. So we will get here two answers. So we have to find two omegas here, when by one taking one and another by 2. So we have to find here 2. So uh, let me take omega 1 and omega 2. So so in derivation, the plus or minus sign we have already taken here. Already we have taken here. So we are not taking it here again, plus or minus. So in that case, so the value will be here plus, here the value will be under root 1.48 or under root that is 0.52. So omega by omega, so this I am taking is omega 1 and this I am taking is omega 2. So in both cases, so the answer for omega 1 will be equal to omega n divided by under root 1.48, that is 1.2166, and omega 2 will be equal to omega n divided by under root 0.52 will be 0.7211. So due to deflection, due to dynamic load of this force is 1 point. Now we have to find omega n also. So to get omega 1 and omega 2, so omega n is nothing but under root k by m. So what is k? So k is stiffness here. So the value of k here is w by y. So that is dynamic load divided by deflection. So the value of k will be nothing but here 36815 Newton per meter. So k we have. And now what is the value of m? So the value of m, that is mass, it is given as 15 kg. So we'll get the value of omega n, so that is 156.66 radian per second. So after we get the value of omega n, so we can find this omega 1 and omega 2. So omega 1 you will get the value as 128.77 radian per second, and omega 2 value you will get 217.257 radian per second. And even if you have to find speed, so the formula for speed, that is omega is equal to twice pi n by 60. So you can use this formula to find n by making subject as of n, like omega into 60 divided by 2 pi is equal to n. So you can find the speeds also for natural frequency omega 1 and omega 2. So that also nn, n1 and n2 you can get. So nn you will get 1496 rpm, n1 you will get 1229.68 rpm, and n2 will get 2074.65 rpm. So this is the whole example, very big example. So you can be asked this example in parts. this whole example is too big to be asked, so it can be asked in parts. So this is the various methods to find critical speeds of the shaft. So I hope you understood. So we'll see few examples and theory in next lecture. So thank you very much.